Today we will be discussing the phenomenon of decoherence. So the problem starts from here. We know everything in the universe is made or everything we know is made up of electrons, protons, and neutrons. And all of those particles, they follow the law of quantum mechanics. They follow the property of superposition, entanglement, measurement, collapse, and whatever we can think of in quantum mechanics. They satisfy all those properties. Why is it that we don't see the quantum effects in our daily life? If everything is made up of the particles which follow the laws of quantum mechanics, why don't we see the quantum mechanical effects in our daily life? And the answer to that is the decoherence. What is decoherence? Decoherence is the environment-induced dynamical destruction of quantum coherence. As you can see, decoherence is the destruction of coherence. And coherence is the property which allows the quantum system to behave like quantum. So the property that they can interfere, the property that the quantum system can be in a superposition of multiple states, and it has the description of a quantum system or quantum state is in terms of amplitude, not in terms of the intensity or probability, is all possible because of coherence. And there are some dynamical processes which destroy this coherence, and hence we do not see any quantum effect in those systems. And how it comes? So what we have done till now, Lindblad master equation and all, those are our more general solutions or general equation for the dynamics of an open quantum system. Decoherence technically decoherence deals with a specific kind of interaction of the system and bath. So let us consider the Hamiltonian H, which is Hs plus Hb plus Hi. So Hs is the free Hamiltonian of the system, Hb is the free Hamiltonian of the bath, and Hi is the interaction between system and bath. So Hs is actually Hs tensor identity, Hb is identity tensor Hb. So here this one is for the bath, and this one is for the system, and Hi is the Hamiltonian for both system and bath. This is the interaction Hamiltonian. Now consider a case where Hs commute with the total Hamiltonian H. Of course, Hs commute with itself, Hs commute with Hb, because Hs and Hb, they act on the different spaces, but Hs need not commute with Hi. But we are putting the condition that H commute with the total Hamiltonian. This implies that Hs commute with the interaction Hamiltonian. Now, if we calculate the expectation value of the Hamiltonian, that will be the average energy of the system at time t, that will be trace of Hs, the time independent Hamiltonian, and the rho at time t, rho s at time t. Okay, and this can also be written as trace of Hs times rho of the total system at time t. Now earlier trace was over only system, now the trace is on system and bath, and this can be written as trace of Hs, and rho of t can be written as exponential of minus I total Hamiltonian H times t, rho at 0 exponential of minus or plus I H times t. And of course, we can use the cyclic property of the operators in the trace. So we can bring this part here, and we get exponential of I H t Hs exponential of minus I H t times the rho of 0. What can we say about this expression? The exponential of IHT, Hs exponential of minus IHT. Since H and Hs commute, this thing will give us just Hs. Because H commutes with Hs, so we can take the exponential of IHT through Hs, and then exponential of IHT times exponential of minus IHT is just identity, and we are left with Hs. So the whole thing will give us Hs times rho 0 and trace of that, and that is expectation value of Hs at time 0. So it means that the average value of the energy does not change with time if Hs commute with H. If this condition is satisfied, then the average energy of the system never changes. Now consider the eigenstates of the system Hamiltonian psi n, where Hs psi n is En psi n. Since Hs commute with the interaction Hamiltonian, we can always write interaction Hamiltonian as sum over n psi n tensor Bn, where Bn are the operators acting on the path. And if you recall, the general form of the interaction Hamiltonian is like this. This expression, this representation will ensure that Hs commute with Hi. Now interaction picture. The interaction Hamiltonian in the interaction picture will be, since our states are not changing with time, so we have psi n tensor Bn of t, where Bn of t is exponential of I hbt, Bn exponential of minus I hbt. Now let the initial state of the system and bath, system plus bath, be capital psi at 0, which is sum over n Cn n, that is an arbitrary state of the system, tensor phi, which is an arbitrary state of the bath. The Cn can be any arbitrary numbers, coefficients, n is psi n here, and we have arbitrary state of the bath. So we are taking the pure state in the beginning. It can be converted to mixed state also, but results will not change. So we are assuming the system and bath both are in the pure state and they are in arbitrary state in the beginning. The time evolution of this state will give us psi 0 going to psi of t, which is exponential of minus I capital Ht, the total Hamiltonian, acting on psi of 0. This operator u of t will be time ordered, exponential of minus I 0 to t, H interaction in the interaction picture is the function of S, ds. Since our interaction picture Hamiltonian is time dependent, so the unitary will be the time ordered exponential of the Hamiltonian. So when we apply psi, either the u of t on psi of 0, we get psi of t, there is a capital psi. Now u of t is time ordered, exponential of minus I 0 to t, sum over n tensor Bn of S ds. And little bit of algebra will convince you that this can be written as sum over n. I'm just writing as shorthand. It's actually the eigenstate of the Hamiltonian system, psi n. So here it will be psi n tensor un of t, where un of t is time ordered, exponential of minus I 0 to t Bn S ds. So un depends on Bn. There is no summation, nothing else. Now if we apply u of t at psi of 0, it means we have sum over n psi n tensor un of t acting on some over M, Cm, psi m tensor phi. The psi n and psi m are orthogonal to each other. So we have Cn, so we have sum over n, Cn, psi n tensor un of t acting on phi. Or we can write it as sum over n, Cn, psi n tensor phi n. So in the beginning, we started with the state of system and bath, which is a product state, an arbitrary state of the system, tensor, and arbitrary state of the bath. But when we apply this unitary evolution on the system and bath together, we are getting an entangled state. Phi n need not be orthogonal, but they are surely independent because UNs are different from each other. So it means this state cannot be decoupled as a state of the system, tensor as a state of the bath in general. There might be some special cases where it is possible, but in general it cannot be decomposed as a state of the system, tensor state of a bath. From here, if you find the state of the system at time t, that will be psi of t, psi of t, and trace over bath. And that will be sum over n, m, cn, cm star, psi n, phi n, psi m, phi m, and trace over bath. And it will be sum over n, m, cn, cm star, psi n, psi m, phi m, phi n. Just to see what happened in the beginning, our rho s at time 0 was sum over n, cn, cm star, psi n, psi m, and rho s at time t is sum over n, cn, cm star, phi m, phi n, psi n, psi n. It means see the element rho nm, rho s, nm element of 0 has gone to rho s nm element at time t, which is phi m, phi n times rho s nm at 0. This is how each element of the density matrix of the system has changed over time. And phi n and phi m, phi n, phi m inner product, this depends on time. This is the time dependent factor. One thing to notice here is that phi n, phi m, they are normalized vectors. So it means phi n is 1. It means the diagonal elements of the row. So rho s nn is cn mod square. And this does not change with time. So the diagonal element of the density matrix does not change with time. This is what keeps the average value of the energy unchanged over time for the system, because the diagonal elements of the density matrix of the state are not changing. The off-diagonal elements have the information about the time and they change with time, and they are given by the time dependence is given by phi m, phi n inner product. In general, the phi n, phi m, phi n mod is given by exponential of gamma nm, which is a function of time. And gamma nm is generally less than 0. It's a negative number. Gamma nmt describes the behavior of the off-diagonal terms and is termed as decoherence function. This is what determines the behavior of the off-diagonal terms, and it is called decoherence function. As t tends to infinity, the off-diagonal terms tends to 0. So the density matrix becomes diagonal. And this is called the complete destruction of the coherence. This t tending to infinity, that off-diagonal terms goes to 0. This is called decoherence. We can see gamma nm of t is given by phi u n of t dagger of t phi. So gamma nm depends on the initial state of the system and the interaction Hamiltonian of the system and bath. Let us consider a specific example of qubits, the two-level system. Here we have the system Hamiltonian, which is minus h bar omega naught over 2 sigma z. We can take the Hamiltonian of the bath as sum over k omega k bk dagger bk, where bk are the annihilation operators of the harmonic oscillator with frequency omega k. The interaction Hamiltonian can be written as sigma z sum over k gk bk dagger plus bk. Actually gk can be complex also, so we can put gk star here. Hs acting on 0 will be minus h bar omega naught. H bar is 1, so we can put h bar to be 1 to be consistent. Omega naught over 2 0. Hs acting on 1 will be omega naught over 2 1, and we can see that Hs and Hi commute. In the interaction picture, the interaction Hamiltonian will look like sigma z sum over k exponential of gk exponential of I omega kt bk dagger plus gk star exponential of minus I omega kt bk. Since the system part does not evolve, we just have the time dependence in the bath operators. From here we can get the time evolution operator ut, which is the time ordered exponential of minus I hit s ds 0 to t, and that will be exponential of minus I 0 to t sigma z sum over k gk exponential of I omega kt bk dagger plus mission conjugate is s here and ds, and this can be written as 0 0 tensor u0 plus 1 1 tensor u1 of t, where u0 of t is time ordered exponential of minus I 0 to t sum over k gk with minus sign, so plus no exponential of minus I or I omega ks bk dagger plus Hermitian conjugate ds, and u1 of t is exponential of plus I. The difference is plus and minus I here only, 0 to t, and the same. If we start with the pure state of the system and the bath, that is sum over n cn psi n, or just n in this case, tensor some state phi of the bath, then the time evolution will give us sum over n cn n tensor un phi, and that can be written as c0 0 tensor U0 acting on phi plus C1 1 tensor U1 acting on phi. And from here we can find that the state of the system at time t, and becomes C0 mod square 0 0 plus C1 mod square 1 1 plus C0 C1 star 0 1 times phi 1 phi 0. This is phi 0 phi 1. Plus C1 star C0 1 0 phi 1 phi 0. No, sorry. This is 1 0 and this is 0 1. This will be the final state of the system at time t, and typically this is given by exponential of minus gamma t. So this is also exponential of minus gamma t, where gamma is the decay rate. So if our state rho s at 0 was C0 mod square, C0 C1 star, C1 C0 star, and C1 mod square, it will go to rho s at time t as C0 mod square, C0 C1 star exponential of minus gamma t, C1 C0 star exponential minus gamma t, and C1 mod square. And as t tends to infinity, exponential minus gamma t goes to 0, and we have rho s at t tending to infinity to be C0 mod square 0 0 C1 mod square. This is how we see the decoherence. This is how we see the off-diagonal terms vanishing, and the only thing left in the state is the density matrix, which are the probabilities of the outcomes of the corresponding states. So C0 mod square is the probability of getting 0 state, and C1 mod square is the probability of getting 1 state. In that way, we loses all the interference term, all the coherence in the system, and this is the reason we do not see any quantum effects in our daily life. In terms of Lindblad operator, if we see the master equation looks like gamma naught n plus 1 sigma z rho sigma z minus half sigma z square rho minus half rho sigma z square plus gamma naught n sigma z rho sigma z minus half sigma z square rho minus half rho sigma z square. Sigma z square is identity. So we have rho dot equals, so when we replace sigma z square with identity, then these two terms are same. We are left with gamma naught 2n plus 1 sigma z rho sigma z minus half rho is 1, so it's minus rho. Sigma z rho sigma z will be rho 1 1 minus rho 1 2 rho 2 1 minus rho 2 2. If rho was rho 1 1 rho 1 2 rho 2 1 rho 2 2, then sigma z rho sigma z will be of this form, and rho, I said rho 1 1 rho 1 2 rho 2 1 rho 2 2. Then we can calculate rho dot equals gamma naught 2n plus 1 0 0 minus 2 rho 1 2 minus 2 rho 2 1. This implies that rho 1 1 dot is 0, rho 2 2 dot is 0, rho 1 2 dot is 2 gamma naught 2n plus 1 times rho 1 2, or rho 1 2 is at time t is exponential of minus gamma t, do the minus sign here, minus gamma t times rho 1 2 at 0. Similarly, rho 2 1, which is rho 1 2 star, will be my exponential of minus gamma t rho 2 1 at time 0. And rho 1 1 and rho 2 2, they do not change in time. Hence, rho of t can be written as rho 1 1, rho 1 2, whatever was the initial state, gamma t rho 2 1, 1 2, and exponential of minus gamma t rho 2 1. This is the same result we got from the other treatment here. And this is the process of decoherence, which is the cause of not observing the quantum effects on ambient temperature in the daily life in the real picture.